Okay, this is remaining notes from 3.5. That was the section we started. We didn't get to the piecewise functions, but we did a little bit of everything else in the section. So I'm going to go through and make sure we understand how to do all the problems. Remember that we talked about how example 1 is not actually on the exam, but that they do show up in your homework. So I'm going to go through, remember the two tests. One is to test for even and one is to test for odd functions. Essentially what you try to prove is that if you plug in a negative x, that it becomes the original function after working it out if you're even. For odd, you say that if I plug in a negative x, the entire function becomes the opposite of what it used to be. So remember, this essentially means that this one has y-axis symmetry, which looks like this across the y-axis, and this one says that it has origin symmetry, which means it flips across both x and y. So let me show you the test. So if I'm doing the even test, I plug in negative x anywhere I see an x. Because an absolute value is the same, there's a rule that says if you have a negative x inside, that's the same as having the positive x inside. Because remember, absolute value always gives you just the positive of the number. Then I can swap this back to being just absolute value of x. That only happens with absolute values. So because this is the original function, that is f of x, that means this definitely passes the even test. Okay? The odd test says that if you plug in a negative x, once you've worked it out, your final step is to try to factor out a negative 1. Now what that does is that changes the signs of both of these pieces. If this is still f of x inside the parentheses, then you're good. If it's not f of x inside, which this time it's not because the signs are wrong, then you're not odd. So this one fails the odd test. So passes the even, fails the odd. We did B in class, so let's look at C. C is kind of interesting because f of negative x, there is no x, so you just put 12. This is essentially the original function, so this is definitely even. If you put in f of negative x to test for odd, you still have just 12, but you still have to do that extra step of pulling out a negative 1. That makes it negative 1 times negative 12 because it always changes the sign when you pull out that negative 1. So this is not negative 1 times f of x because negative 12 was not the original function. So this one again does not pass the odd test. D, we plug in negative x. This is to test for even. We work out any sign, so if you square something, it turns into a positive. Negative times negative is also a positive. This is not the original function. It does not match every single sign. So that means not even. So even this time is an x. Odd, we put in negative x again. And notice the steps for even and odd are exactly the same until you go to pull out that negative 1. Sorry, my plus 1's not showing up. Plus 1. So this would be f of negative x equals 3x squared plus 5x plus 1, but then we try to pull out a negative 1. What that does is changes all the signs, which means that this is not negative 1 times f of x. So again, this one fails both. So it would be neither. That just means if you graph this, it doesn't have y-axis symmetry and it doesn't have origin symmetry. Doesn't mean it doesn't have some other kind of symmetry, but it just doesn't have those. And then E is the last one. If I do f of negative x for even, we put in negative x in for all the x's. If you cube a negative, it is going to be negative. If you have this is a negative times negative, so that's a positive 1 over x. Notice that that is not the original function. For the odd test, we do the same exact steps, except we try to pull a negative 1 out at the end. So this was negative x cubed plus 1 over x. If I pull out a -1, it becomes x cubed minus 1 over x. That is -1 times f of x. So this one is odd. Okay, this is just a summary of all those translations that we learned. We learned essentially, and I'll just summarize them here, if you add something to the end or subtract it to the end after the parent function, that makes your graph either move up or down vertically. If you add or subtract something inside the function, so that means like if you're squaring something, it happens before you square it, then that is what we call, remember, a horizontal shift. And it's always opposite to what you think. So a negative actually moves you to the right if it's inside, and a positive moves you to the left. So notice the blue one went right, the blue one went left. Then we had, what if there's a number out front? So notice if I have a number in front of my parent, if that number is greater than 1, then you get what's called a stretch. Your graph is the same shape, but it is stretched. In other words, these get multiplied by that C value, those Y values do. If you have something between 0 and 1, notice it makes this graph compressed. It's shorter in all locations. So this is a stretch and this is a compress. Now these are both in the Y direction because that C was happening outside of the function. Okay. If the C happens inside the function, so notice here it's inside. Notice that if it is greater than 1 and if it is between 0 and 1, those are still the same parameters, but they do different things. If it's bigger than 1, it's going to compress you in. Compress in the x direction. And if it is between 0 and 1, in other words, a fraction, you're going to stretch in the x direction. Anything that happens inside of a function, in other words, like before you square or before you apply an absolute value, it always does the opposite of what you think. So if something looks smaller, it's actually going to be bigger. If something is adding, it's actually really subtracting. So you have to think opposite world when you're inside the function. And always those things affect x. Anything that happens outside of the function, in other words, multiplied out in front or added or subtracted at the end, that means it's affecting y. The last type of transformations, which I don't know where they went, is if it was a negative in front. Maybe I didn't have that group in here. If it's a negative in front or, yeah, there it is. I just didn't have pictures. If you have a negative in front of your function, that means you're going to reflect over the x-axis. If you have the negative inside the function, which is right here, so if the negative happens inside the function, you're going to reflect over the y-axis. So those are two other types of transformations. Okay, we did some of these in class, but just because I did different ones for different groups, I'm going to try to go through and just work through this whole assignment. I'll probably make this a two-part video, so I'll get through some of these and then pause and then start part 2. So that way you can kind of watch this in 2 different settings if you need to. So for this one, the thing we had to say is that you had to know what parent shapes were involved. When you see a square, that is a U-shaped graph. And the typical x-squared graph, without any adjustments to it, has these 3 key points. This is just what you get if you plug in -1, 1, and 0. Okay, -1, 1, 0 squared is 0, 1 squared is 1. This is a vertical shift because it's added after they squared, which means it does exactly what you think. It's going to be up 3. Another way of thinking of that is plus 3 to the y value. So if you take this negative 1, 1, and you go up 1, 2, 3, now notice it's at negative 1, 4. The negative 1 didn't change, but we went up 3. 0, 0 would go up 1, 2, 3, and 1, 1 would also go up 1, 2, 3. And you have your same generic U shape. Absolute value of x minus 1, so we have to know what the general shape of an absolute value is, and these are all at the bottom of this document if you need to refresh on those. So this is what we have anytime you have an absolute value of x. It's this general V shape. It's 0, 0, negative 1, 1, and 1, 1. Notice the same 3 points that you had for x squared, but because this is an absolute value, it comes in at a sharp V. So this one has something happening after the absolute value again. So that means this is a vertical shift, and it's going to be down 1. So here's 0, 0, so down 1, 1, 1, down 1, negative 1, 1, down 1. There are my new 3 points. So the whole graph got shifted down 1. Then we get into the ones that have something happening before they do the actual parent shape. So notice these, we're having this minus inside before we cube. By the way, the parent shape for x cubed is a parabola that got confused, essentially. It's going half of it's up, half of it's down. You get this kind of cubed shape here. So this is 1, 1, 0, 0, and negative 1, negative 1. The reason this goes down is because negative 1 cubed is still negative 1. Now anytime you have something inside, it's going to affect x, and it does the opposite to what you think. So since this is a minus 2, I'm actually going to add 2 to all x's, which means we're going to be moving right 2. So negative 1, move right 1, 2. 0, 0, move right 1, 2. 1, 1, move right 1, 2. Notice same shape, shifted 2 to the right. Okay, this one is the cubed root of x, and again this is happening inside before they cubed rooted. So that's going to be what we call, remember, a horizontal shift again. And for a horizontal shift, first of all, you have to know the parent shape. So there's 5 parents that you have to know. We've already seen 3 of them. Cubed root of x looks similar to the one we just did, except it is shaped a little bit differently. It goes like this and this. Negatives still stay negative. 0 is still, cubed root of 0 is still 0, and positives, cubed root, are still positive. You're doing the same general shape, it's just on its side essentially now. Positives stay positives, negatives stay negatives. So then this is saying plus 1 to x, which means we actually need to subtract 1 to all x's, because you always do opposite to what you see inside. So that means we're moving to the left. So negative 1, left 1. 0, 0, left 1. 1, 1, left 1. And then there's the same general shape. Okay, and our fifth and final parent that you have to be familiar with, because I've shown you 4 so far. Notice we've had x squared, absolute value of x, x cubed, cubed root of x, and then we have square root of x. So square root of x by itself looks like this. You have 0, 0, because that's the square root of 0. Square root of 1 is 1. And square root of 4 is another perfect square, is 2. So there's my 3 key points. So you kind of get this parabola on its side, and only half of it's there. When you have a negative out front of your parent, so notice that's out front, that's going to affect y. It changes y, so it's changing its sign. If you change all of the signs of your y's, they go upside down. This means you reflect over the x-axis. So you get these same 3 points. This one's going to stay where it is because it's already on the x-axis, but they're down below. So this would be 0, 0, 1, negative 1, and 4, negative 2. So that's that one. If the negative happens inside, same shape again, this is still square root of x, so same shape there. This is going to change x's sign. If you change all of your x's, you flip across the y-axis. So reflect over the y-axis. So again, notice that means this guy is going to go this direction, because if this is my y-axis, it's going to flip over. So we get 0, 0, negative 1, 1, and negative 4, 2. So notice the same guy just flipped across the y-axis. Okay, then we get into the ones that have stretching or compressing. So when dealing with these, we have to talk about, is it inside or outside, because that does determine how we interpret the information. So notice this is that x cubed shape, which we already know looks like this. Negative 1, 0, 0, and 1, 1. Those are the three main points. A 2 on the outside, because notice that's not being cubed. There's no parentheses around that 2. Means that you are stretching your y values. Now that's because this guy is greater than 1. If this was between 0 and 1, we would say we were compressing our y values. So the way this is this is doubling or times 2 each y. So think about this. This is negative 1, negative 1. I'm going to do it point by point. 0, 0, and 1, 1. If I times each y by 2, that gives me negative 1 staying the same on the x's, 0 stays the same on the x's, because none of the x's are being changed, and 1 stays the same. If I multiply all the y's by 2, I get negative 2, 0, and 2. So notice you kind of do need to do these stretches and compressions by a point comparison. So this is negative 1, negative 2, 0, 0 is still where it's at, and 1, positive 2. Notice that I've got a thinner x cubed than what I normally have. So this is a little bit narrower or thinner. Okay, so if we put a fraction in front, like 1/4, that's still going to be a type of stretch or compression in the y direction, but this is actually going to be a compression this time because it's between 0 and 1, and it's out front, and it's not being squared. So remember, our squared parent is 0, 0, 1, 1, and negative 1, 1. Okay, so if we're going to take, this is again affecting y, so we're going to take 1/4 of each y. So my 3 points, I write them down. I realize that x's are not being affected, so I can rewrite the x's right away. But I'm going to take 1/4 of each y, so that makes this 1/4. 1/4 of 0 is still 0, and this makes this 1/4. So notice that's 0, 0, negative 1/4, and 1/4. Notice my parabola is taking a lot longer to grow. I could do more points if I want, but essentially if you're got a fraction in front that's less than 1 but bigger than 0, you're going to be making a wider graph. So this is a compression in the y direction because you're squishing down how fast they grow. And then what happens if the number's inside? So notice this is the x cubed shape because of the cube on the outside. 0, 0, 1, 1. That's a horrible ordered pair. 1, 1. And negative 1, negative 1. That's x cubed. When it's inside, it happens to x. And remember, anything that happens to x is opposite of what we think. So instead of multiplying by 2, we do the reciprocal. We are going to take half of x. So take your 3 points and take half of each x. So that makes that a half, but the y's don't change. Negative a half, but the y doesn't change. Half of 0 is still 0. So this would be a half positive 1, a half negative 1, and 0, 0. Notice this looks a lot like when you had a 2 on the outside, because it looks like it's being stretched. But when we talk about this, we say this is a compression in the x direction because the x's have been squished. Because think about this as the x is getting pushed in from both sides. And then what happens if we have a fraction inside that's less than essentially 1? So this, notice, is between 0 and 1. And when we say it's between, we don't care if there's a negative sign there or not. We're looking at just the number value. If there's a negative inside as well, that means there's also a reflection happening. So anytime you see a number and a negative sign, when it's in either inside or right in front, that's actually two transformations at the same time. So this is actually going to be a stretch on x, because we do opposite of what we see, and we're going to do 9 over 1 of each x. So in other words, you're going to times each x by 9. So the square root function, remember the shape of that. If you don't know your square root function shape, it's impossible to get the graph from a transformation. You had 0, 0, 1, 1, and 4, 2. Those were the 3 points. So if we times each x by 9, that makes 0, 0, 9, 1, and 36, 2. So notice that's going to give me some really crazy points way out in space. So very, very stretched thin. So notice this has been stretched on the x, but it's compressed on the y. So this is a stretch on the x-axis, or the x direction, I should say. Doesn't always have to be on the axis. Okay, and then this last group, before we're going to take a splitting minute, because I'm going to split up before I go on to example 3 and make it a part 2 of the video, is these transformations that have multiple ones. This has 2 transformations, and it's an x squared shape, so we're looking at that. This is up 1, and this is right 3. Now when doing these, you have to do the ones that are closest to x first. So we are going to take this. I'm going to get my 3 key points for a parabola, and I'm going to go right 3 for the point first and then up 1. So 0, 0, right 1, 2, 3, then up 1. So there's that new home. Negative 1, 1, I'm going to go right 1, 2, 3, and then up 1. Positive 1, 1, I'm going to start here and go right 1, 2, 3, up 1. So I counted right 3 from each individual original point and then up 1, because that's like the order of operations for this. Okay, so for this next one we have a square root, and we have an x plus 1 underneath, so that means we're actually going to have a left 1. Remember, it's always opposite of what you see when inside. And then this negative on the outside tells me we're going to reflect over the x-axis, actually, because that means our y's changed signs. And so because this is closer to the x, it's inside the function, it goes first, and then it goes second for this. So, and that will be important. If I ask you to write out directions for what to do for a function, you need to tell me the directions in the order of operations. So remember, our square root of x is 0, 0, 1, 1, and 4, 2. Those are our 3 key points. So 0, 0, I go left 1, I'm on the x-axis. If you're on the x-axis, you can't reflect because you're already there for the x-axis reflection. So then I'm going to go for positive 1, 1. I go left 1, and then a reflection means you move to the same location under the x-axis. So it's actually down here at 0, negative 1. And then for 4, 2, we're at 4, 2. We're going to go left 1. Now we're at 3, 2. So after we reflect, we'll be at 3, negative 2. So notice this graph is now left 1 from the original and upside down. And then this final one is 2 different types of transformations again. This is down 2, and this is a compress in the y direction. because it's not in a parentheses, so it's the y direction. This one would still come first because it's closest to x, and it would be done first if you were doing an evaluation. So let's think about x cubed. X cubed, remember, looks like this, with the points -1, -1, 0, 0, and 1, 1. I'm going to show you how to take these 3 points and just do a transformation of the numbers without actually plotting it out and pointing. So for this first transformation, we're going to be doing the the compression, sorry, not a negative sign. The compress in the y direction. That means you do exactly what you see to the y value. We're going to take half of all the y values. So that makes this a -1/2. Half of 0 would still be half of 0, and then half of 1 is a half. Notice the x's don't change on this part. You're compressing in the y direction. And then we're going to take those and we're going to take everything down 2. So that means you subtract 2 from y. So this would be -1, -2.5, 0, -2, and 1, -1.5. So -1, -2.5 is right about here, 0, -2, and 1, -1.5. Notice a lot flatter right there in the middle. That means this has been squished down. So that is a compression and then a shift down. Okay, so that's a good place to stop part 1 of this video, because then I can do the other part as part 2. We will still have piecewise functions to talk about first thing in our next class session.